Welcome to lecture 12 of Power System Protection course. In the previous lecture, in lecture 11, we discussed about the directional relay in detail, and also we have seen how the directional relay can be implemented for phase faults and for earth faults, for ground faults in a three-phase feeder. Already we have seen this. And in this lecture we'll see in detail a little bit more about overcurrent protection, which is associated with the directional relay. So let us start with, let us summarize the directional relay phase fault, how the relay will be excited for different phase faults, right? So already we have seen this. Let us just rewind or revise this. So type of connection, different type of connection for different type of phase faults, right? First, the phase fault involving phase A, right? So the current will feed to the relay is IA, that is the phase A current, and voltage is VB. So we call this 90-degree connection. And similarly, for 30-degree connection will feed phase A current and voltage VAC, that is the line voltage across phase A and C. Similarly, for 60-degree connection will feed current of phase A, and the phasor sum of the voltage is VAC plus VBC. Okay, similarly, the phase faults involving phase B, we know the 90-degree connection, 30-degree connection, 60-degree connection. To why we call this 90-degree, 30-degree, 60-degree. Already we discussed these things already in the last class, right? So similarly, for phase faults involving phase B, we'll have current IV and VCA because they are making 90-degree with each other. VCA is lagging 90-degree to IV. And similarly for 30-degree connection, IB, and we'll choose IB and VBA. For 60-degree connection, IB and VBA plus VCA. Similarly, phase faults involving phase C will have current IC and VAV for 90-degree connection, and current IC and VCV will be for 30-degree connection, and current IC and the phasor sum of voltage VCV plus VAV will be for 60-degree connection. So this is just summary of all the phase faults for how the relay will be excited. And then we have also seen the directional ground fault protection. Already we have seen this, that for ground fault we have to feed the sum of the phasor sum of all the phase voltages VA, VB, VC to the directional relay potential coil, and similarly will feed the sum of the currents IA plus IB plus IC, that is 3I naught, to the current coil of the relay, directional relay. So already we have seen these phasor diagrams and how it will operate, and how the 3IO that will lie in the trip region, and how the reverse current will lie in the restraining region. Already we have discussed this, and let us go ahead. So now we'll see the directional overcurrent protection of a three-phase feeder, how practically it looks like. We have seen for different phase faults different how to excite the relay for different phase faults and ground faults, and now we'll see how practically a directional overcurrent relay, overcurrent protection, can be implemented in a three-phase feeder. So this is your three-phase feeder, where we can see we have three phases. They are associated with three lines, and with each line we have CTs having ratio n is to 1, right? Each of the CT ratio in n is to 1. So therefore the current through the secondary coil of the C2 will be IA by N, IB by N, and IC by N, right? And that will flow through the different relay coils, right? Now, for phase fault, we have put the relay coils for phase C and phase A, right? Phase fault for phase A and phase C, they're excited in the phases, and phase V, that is third relay coil is put in the ground wire, right? Okay, we can see here. So now how it will excite, let us see. For phase faults, for phase fault overcurrent relay, RA and RC will excite, right? So RA is this and RC is this. So both will excite for the phase faults, different phase faults. Already we have seen the phase faults. Phase faults are the faults which involve the phases. Any two phases, then we call it phase faults. If a single phase is grounded or short circuited, that we call the ground fault, right? Okay. So this is how for the phase fault overcurrent relay, RA and RC will excite, and for ground fault overcurrent relay, RG will excite. Similarly, for the directional element or for the directional purpose or directional overcurrent relay, these two relay coil will excite. One is one potential coil of RC and other potential coil of RA, which are fed by both VVC and VAV, right? Okay, already we have seen these are the 90-degree connections, right? And how we'll get VAV and VVC from here, right? From the potential transformer, from the voltage transformer. Here we have the voltage transformer. From here we'll get VVC. VVC will be fed to this, and VAV will be fed here, right? It will be fed here at this point. Okay. So similarly, in the ground where we have for the protection of ground fault, we have a relay that is connected to ground wire, and that ground fault overcurrent relay will be RG, which is fed with 3IO. 3IO is nothing but this is IA plus IB plus IC, right? If we'll see, this is IA plus IB plus IC, which is passing through the ground wire, and similarly we'll feed the potential coil of this relay, that is RG directional, by 3VO. So 3VO, how we'll get? 3VO will be get from these potential transformers. Here we can see that these are the transformers. They're connected transformer phase windings, three-phase transformers phase windings, right? There the primary side is connected in parallel, and the secondary side is connected in series. So as it is connected in series, so all the voltages, that is VA plus VV plus VC, will be added together, and it will give us the, sorry, this is VC. So VC will be added, and that will give us 3VO, and it is in fact fed here, right, to this. So this is fed here, right? So now it will excite the obviously it will excite the directional element and the overcurrent element. They will excite the trip coil contacts, and finally it will give the signal, trip signal, to the circuit breaker. Circuit breaker is connected here, right? Okay, so therefore all types of sound faults are covered under this protection scheme. Right, all types of sound faults we have seen. All types of phase faults and the ground faults are covered under this protection scheme. Then phase faults associated with phase B will be covered under the scheme for AB or BC faults, right? So whatever phase fault that will be associated with phase B, that will be covered under the schemes, that is under AB or BC faults. Okay, either AB or BC we can consider. So however, ground faults associated with phase B will be covered under 3VO and 3IO scheme. Ground fault associated with phase B is B to G, right? So phase B to ground fault, so B to G fault. So it will be covered under 3VO and 3IO scheme by this relay, right? By this ground fault relay. Okay, so this is how we protect the three-phase feeder, because in the relay we have three coils, three current coil and three voltage coil. We have to ultimately we have to arrange these three coils for the protection of all kind of protection, all kind of sound fault protection. Therefore, this is the arrangement for better protection of a three-phase feeder. Okay, so let us see how this directional protection can be used under non-fault conditions. Non-fault condition means when the reverse power flow happens to occur. Reverse power flow, many times it happens because under the circumstance when the synchronous generator is connected and suddenly there is a load shedding. So suddenly, because of the load shedding, uh, it doesn't supply power, or some fault happens in the generator, synchronous generator, then reverse power flows to the synchronous generator. At that point, we need a reverse power relay which detects the power flow in the reverse direction, and it automatically isolates the faulty section or the faulty element from the power system. So how it works in fact. So this is the power directional relay. In fact, the constructional feature and operational aspects are similar or same as the directional relay, directional overcurrent relay. So here, if we are feeding VCA and IA, let us feed VCA and IA, right, with an MTA of 30°. So how the phasor diagram will look like? Let us see. So now if we'll plot the phasor diagram under normal condition, the current flows in this direction, right? That is IA under normal condition, and this is VAC, and that is making an angle of 30°, right? And our objective is when the current is flowing in the forward direction normally without any fault, there should not be any trip, right? No trip. That is the forward power flow. Okay. Now, for the reverse power flow means your I, the current will flow in the opposite direction, right? So that will, let us say I2 is the reverse current flowing in phase A. So that will be in opposite direction, and under this condition, your relay should trip. And let us see how it operates, right? So if we'll plot the phasor diagram, in fact, so this will be your VCA. This is VCA already given, right? And VCA is fed to the pressure coil. This is to your pressure coil, right? This is to your current coil. So as VCA is made, so if we'll make this as IPC, okay, let us say this is IPC. Now your MTA will be here somehow, right? It will be perpendicular to, it will lie along with I2, okay? It will lie along with I2. So this is your maximum torque line, right? MTL. So maximum torque line. So your maximum torque line will be perpendicular to IPC. So therefore this will be MTL. Now if your, because this is making an so this will be, if we'll take tau, it will be around 30°, right? Okay. So therefore MTA is considered here 30°, and now we can see here that for forward power flow, this is not tripping. So this is in the restraining region, right? And this is your trip region, right? Because here the MTA is this, and perpendicular to this is your line demarcating the trip and the restraining region, right? So this line is your, in fact, segregating between the trip region and the restraining region. So this is your restraining region, right? Restrain, and this is trip. Okay. So therefore, when reverse power flow happens, so it will trip. Okay. So this is how your reverse power relay reverse power relay operates. So without any fault also it operates. Okay, so already we talked about how it will be implemented and how it can act as a reverse power relay, and then we'll see how the directional overcurrent relay we can coordinate in a mesh network if we have a mesh network, because generally there are many distribution networks, they're meshed in the structure. So we need to see there, because there will be many circuit breakers and many relays, how to coordinate, because it's really challenging to coordinate the relays in a mesh network rather than in a in a radial network, right? So let us see, this is a mesh network what we are seeing here, right? It has 4 buses and it is marked here bus. Let us say this is bus number 1, so this is bus 1 and this is your bus 2. Okay, bus 2, and this is your bus 3, and this is your bus 4. Okay, so now these are the 4 buses and they are interconnected together, and there are many lines, 1 2 3 4, 4 lines, and we need at least for each line 2 circuit breaker, 2 relays, so around 8 relays, right, for protection of these lines, right? So then the question is how to coordinate these relays, because we don't know, because in radial feeder what we do is start from the tail end and we go to the source end. And here how we'll start with, from which point we'll start, that is a main confusion also, right? How we'll start with, so we can start from any relay. We can see here for let us consider fault F1, right, at bus 1, fault F1. So for this fault we'll have two protection. It will be protected by 2 relays. One is your R2. So R2 will protect this section by in anti-clockwise direction, right, like this, in anti-clockwise direction. And if we'll see another relay, that is R6, so R6 also will protect this faulty section in clockwise direction, right? Okay, so therefore we have 2 relays here for each of the fault as primary protection. One is in anti-clockwise direction and one is in clockwise direction. Similarly it will be for each of the faults. Okay, and also for each relay another relay becomes the backup relay, right? So therefore we need to consider the primary protection and the backup protection both in this case. So let us see how we can do this, right? So let us consider fault at bus 1 F1. Now this R2 will act as primary relay for F1, right? Okay, and for R2, R1 will act as in anti-clockwise. Let us write it here, in anti-clockwise direction. In anti-clockwise direction, R2 will be acting as primary protection for F1, right? And to R2, R1 will be the backup protection, right? Backup to R2, right? Similarly, for R1, right? R1 will act as primary for F2, for this F2 fault at bus 2, and for R1, R4 will act as backup. Okay, this is in anti-clockwise direction, right? So similarly for fault F3, R4 will act as primary protection, and to R4, R3 will act as your backup protection, right? Okay, similarly for fault at F4, R3 will act as primary protection, and to R3, R2 will act as the backup protection. This is your cycle, right? This is in anti-clockwise. Then similarly for clockwise, we will see, clockwise also we will see for fault F1, R6 will act as primary protection, and to R6, R5 will act as the backup protection. Similarly for F4, for fault 4, F4 at bus 4, your R5 will act as the primary protection, and to R5, R8 will act as the backup protection. Similarly, for F3, fault F3, your R8 will act as primary protection, and to R8, R7 will act as the backup protection. Similarly, for F2, your R7 will act as the primary protection, and your R6 will act as the backup protection to R7. So this is in clockwise direction, right? Okay. So now let us see the table which summarizes the anti-clockwise and clockwise protection. So now we'll see the fault current seen by the primary and backup relay pairs. So fault current is given here. Okay. So the remote bus faults at F1, F2, F3 and F4. So we have considered here 4 faults, and the current seen by the primary relay. So R2 is the primary relay for F1, and the fault current will be seen by R2 will be 639. Maximum fault current will be 639 ampere. And similarly, R1 current seen by the backup relay will be 152 ampere. It will reduce, right? Okay. And similarly for F2, R1 will act as primary protection, and the current seen by R1 will be 1652 ampere, and R4 will act as the backup protection. It will see a current of 391 ampere fault current. Similarly, R4 will act as the primary protection for F3, and the fault current seen by R4 is 1097 ampere, and R3 will be the backup protection for R4, and the current seen by R3 is 140 ampere. Similarly, R3 will act as the primary protection for F4, and R2 will act as a backup protection for R3. R3 will see a current of 937 ampere fault current, and R2 will see a fault current of 142 ampere. Similarly, in clockwise direction, we have these combinations for F1, R6, R5, and they see different currents, R7, R6, R8, R7 for F3, then R5, R8 for F4. So these are the clockwise direction protection scheme, and this is anti-clockwise protection scheme. Now the question is, if we know the pickup value we can choose. Already we know how we can choose. Pickup value can be chosen between the over 25% overload, right? Overload less than equal to pickup current less than IF minimum. So by using this criteria, already we have the pickup current is chosen and it is shown in the table. Okay, now you can see the pickup current for different relays. For R1 the pickup current is 60 ampere, for R2 it is 80 ampere, for R3 it is 60 ampere. So it is based on the loading and the minimum fault current. For R4 it is 160 ampere, for R5 it is 80 ampere, for R6 it is 160 ampere, for R7 it is 128 ampere, for R8 it is 100 ampere. Now already we decided the pickup values. Now the question is how to choose the TMS setting, that is the time multiplier setting, right? TMS. So we need to find the TMS for all the relays, all the 8 relays we need to find. So how we'll find? Now the question how we'll find, let us see how we'll find. So the normal range of the TMS, generally there is a range of TMS. Previous example we have seen the range 0.1 to 1, right? Like here the range is 0.025 to 1.2, the range, right? So this is the minimum value we can set in TMS dial, right? And the maximum value we can set is 1.2. So now let us start with, so how we'll do then? Okay, so there is a general algorithm for setting TMS in a mesh network. So what is that general algorithm? Let us see that algorithm. In step 1, we consider a set of relays either in clockwise or in anti-clockwise. So first we'll set the clockwise, then we'll set the anti-clockwise. Let us consider. So first we need to set one set for clockwise or another. Then we'll set another set for the anti-clockwise, right? Already we have seen the set of uh, relays for clockwise and anti-clockwise. So set of relays for anti-clockwise is R2, R1, R4, R3, and these are the set of relays for anti-clockwise. And for clockwise, R6, R5, R6, R5, then your R7, R8. Okay, so these are the relays for a clockwise direction, right? So now we need to set, using this algorithm, general algorithm, we need to set the TMS in all these relays. In step 2, what we do, consider one relay out of one set. Then we'll consider only one relay. Any randomly you can choose any one relay out of that set and assume that the TMS value within the provided range. So any value we can assume the TMS setting. There is no hard and fast rule that we choose the minimum value, not hard and fast. So we can choose any value between that range. Then we calculate the operating time for that relay. Then using the standard formula, standard equation that is given in the IEEE or IEC, whatever relay is provided, whatever relay is connected, using those relays, we can equations, we can uh, find the operating time for that particular relay. Then in step 3, we calculate the operating time for the backup relay. We know the backup relay for that relay, and by adding the CTI, the coordination time interval, then we'll get the operating time for the backup relay. Okay. Then in step 4, with the calculated operating time and fault current seen as the backup relay, compute the TMS setting for the same relay. Okay, now the operating time of the backup relay we know, and the fault current seen by the backup relay we know, and we can compute the TMS using those standard equations, okay, for that backup relay. Now in step 5, with the calculated TMS, whatever we calculated the TMS value in step 4 for the backup relay, now compute the operating time of that relay when it acts as the primary relay to a particular fault. So for the primary protection, how much time it takes. So let us calculate that. Then in step 6, go to step 3 to calculate the operating time, then your TMS setting again. So again from step 3 to 5 it is repeated until the process of TMS setting reaches to relay it started with. So okay, this step goes on until we reach the relay where we started, right? Then in step 7, the TMS value at the end of the iteration is matched with the previous iteration. If the deviation is very high, then repeat step 3 to 7, else end the iteration to obtain the final results. Okay, else we get the final result. If your deviation from the present iteration value to the uh, previous iteration value is not very small, it is, then we can stop the iteration and we'll get the final result for one set of relay. For one set means for clockwise or anti-clockwise, whatever you have considered in the beginning. Then for computing the setting of other set which is left, we can repeat the steps 2 to 7. So again we'll repeat the step 2 to 7, right? Again we need to repeat these steps and again we'll find the setting for the other set of the relays. So this is a general algorithm for setting TMS in a mesh network. So let us then see how we can solve this problem. The problem is given here, right? Already the problem is given, the fault current, maximum fault current is given, that is seen by each of the relay as primary and backup relay, and the pickup values are given. Now how we'll find the TMS setting? Let us see. Using this algorithm we can find the setting of TMS. So let us see. So it is really iterative, as we see from the algorithm, as we have seen in the algorithm, that is iterative till it converges, till the value of the setting in the present iteration is not much deviated from the previous iteration, right? So therefore let us start with iteration 1. So for fault at F1 where R2 acts as primary, already we have seen that for fault F1 R2 acts as the primary relay, and for that let us find the time of operation using the standard inverse relay characteristic. This is the IEC standard inverse relay characteristic, right? Okay, and so this formula is TMS into 0.14 by the PSM plug setting multiplied to the power 0.02 minus 1, right? This is the formula. The formula is T operating for standard. Already we have seen this. IEC standard inverse relay is TMS into 0.14 divided by PSM to the power 0.02 minus 1. So PSM is nothing but uh, uh, your fault current divided by the pickup current, that is the plug setting pickup current. Okay. So now we can see we can find the operating time just by substituting the TMS value. TMS setting we have to choose, then any random value we can choose between 0.025 to 1.2, and 0.14 is given, and plug setting multiplier from the fault current will find, because the fault current is given and the pickup current is given, right? Where we can see here the pickup current is 80 ampere, fault current is 639 ampere. Now let us substitute this, and the TMS value chosen here is 0.05. Okay, now just substituting these values, we got the operating time for the relay 2 TR2 is 0.165 second. Okay, now for fault at F1, relay 1 R1 will back up to R2. Already we have seen this, right? So hence the time of operation of R1 will be TR2, that is the operation time of relay 2, plus CTI, that is coordination time interval, where CTI is the coordination time interval and CTI here chosen as 0.3 second. Okay, so it depends upon the circuit breaker operation time and the relay operation time. Based on that, we choose the CTI. Already we have seen in the previous examples what we discussed in the previous classes. And here the CTI is chosen as 0.3 second. Now adding the 0.3 second with the operation time of relay R2, we got 0.465 second, which is in fact the time of operation required by relay R1 when it is acting as the backup relay, right? Okay, so when it is acting as the backup relay, this time is required, right? Now from this time of operation we can find the TMS setting of R1, relay R1. So now let us substitute this operation time of R1 in the standard equation, and substituting all these values. I, we know it is 152 ampere. It is seen by relay R1 as backup relay, and IS is your pickup current. So we can substitute here I and IS, and then we can find the TMS R1, that is the TMS setting of relay R1. So from this equation we will find TMS equal to 0.0623 for relay R1. Okay, so this will be the TMS setting for relay R1. Now using this TMS setting of relay R1, we'll find the relay operation time of R1 for the primary when it will act as a primary protection for the fault F2, right? So for fault at F2, R1 acts as the primary protection, okay, for a primary protection. So for that, how much time it takes R1, right? Just by putting the TMS setting, whatever we found, right? TMS setting, then the pickup current and the fault current, then we found that the operation time of relay R1 when it is acting as the primary relay for F2 is 0.127 second. Okay. Now relay R4 will back up. Now we found the time of operation of relay R1 when it is acting as primary relay for F2. Now R4 will be the backup for R1 for fault F2. Now similarly we'll find R4 operation time by just adding the coordination time interval. So in the operation time of relay R1, just by adding the CTI, will give CTI is taken as point, considered here as 0.3 second, and the primary relay operation time for R1 as primary relay is TR1, which is 0.127. So 0.127 plus 0.3 will give us 0.427 second, and this is the time required by relay R4 when it is acting as a backup relay for R1 for fault F2. Okay. Now using this time, again we'll find the TMS setting for relay R4. So let us find the TMS setting. So TMS setting for relay R4 can be found from this equation just by substituting the time of operation for R4 and the current seen, backup current seen by, for backup fault current seen by R4 and the pickup current of R4, right? So just by substituting we'll find TMS. So TMS for R4 will be 0.055. Okay. Now using this TMS value, now we can find the time of operation of relay R4 when it is acting as a primary relay for a particular fault, right? So that fault is F3, right? So for F3, the relay 4 will act as a primary relay, and for that, what is the time of operation? We can, using this equation, we can find again the time of operation of relay 4 when it is acting as a primary relay to the fault F3. Okay, so now we can see here relay R3 is acting as the backup to R4 for so therefore we can find the time of operation of relay R3 just by adding the CTI to the operating time of that is the primary operating time of R4 when it is acting as a primary relay. So just by adding we'll get 0.496 second, that is the time of operation for R3. This is the backup protection time for R3 to R4, right? Now for a fault at F3, R3 has to back up R4. So then we can find the TMS setting for R3 by using the time of operation and the fault current seen, backup fault current seen by relay R3 and the pickup current. We can find the TMS setting of R3. So TMS setting of R3 will be 0.0605, right? Similarly, for fault at F4, R3 will act as primary relay, and therefore the time of operation of R3 for the primary protection we can find from the standard equation, and you just substituting the current values, fault current seen by the relay R3 and the pickup current, we can see that the TR3 will be 0.15 second, right? And for fault at F4, R2 will be the backup to R3, right? So therefore we need to find from this equation, from the standard equation, we'll find the backup operating time of R2. So time of operation, which is for the backup protection, will be TR3. This is TR3 plus CTI, right? That is the operating time of relay 3 as for primary protection at fault F3 plus coordination time interval, that will give us the time of operation of R2 when it is acting as a backup relay to R3. So that is 0.45 second. So using this, we can find already we have chosen a TMS setting for R2 previously, that is 0.05, that is TMS R2, right? Already we choose this. Now again we are going to calculate the TMS setting of R2 from this time of operation. Okay. Now whatever value we'll calculate and whatever value we have chosen initially, that must match. If it will not match, then we'll go for the next iteration. Okay. So let us calculate the TMS value of R2. So it is found 0.037. It is in fact not matching. There is a huge deviation between 0.05 and 0.037. So therefore we'll go for next iteration. We had assumed the value of 0.05 per TMS R2, but now the value has changed to this. Therefore, let us update TMS of R2 to this. So now we'll update the TMS of R2 as 0.037 and we'll go for the next iteration. So with the value of 0.037, we'll go for the next iteration. In the similar way, we'll calculate all the values again. Again the settings, TMS setting of all the relay, like relay R1, then R2, R1, then R3, R4, all will change, right? So finally, we'll get again we'll come to the TMS setting of R2. Okay, here we can see we're calculating again the TMS setting of R4, then we're again calculating TMS setting of R3, right? Here we're calculating. So TMS we found here for R4 is 0.0535. Here again TMS we found 0.0599, right? Now again we calculated for R2 time of operation, then we found again TMS for R2, which we found to be 0.369, right, in the second iteration. And in the first iteration, in the finally in the first iteration, we chosen the value, calculated value as 0.037, right? Okay, and it was in fact there is a deviation between 0.037. So in the end of the first iteration, we found TMS R2 as 0.037, right? And now at the end of the second iteration, we found the TMS value is 0.0369. So there is a deviation, little deviation. Now let us go for the third iteration, then we'll see. Let us update the TMS of R2 to this new value of 0.0369 and let us repeat the iteration. Okay. So now going for the iteration 3. So again we'll go for iteration for different faults. Again we'll update the TMS values. So we found TMS of R1 is here this. Again TMS R4 is calculated this, right? Again we calculated TMS of R3 as this, right? So then finally again we calculated TMS of R2, which is found to be 0.0369 and which is same as the result of iteration 2. So finally we can see that the end result of iteration 2 and the end result of iteration 3 are matching exactly. Now we can say that the values, the TMS setting, whatever we achieved after iteration 3, there is no deviation with the previous iteration. So we can fix these TMS settings in the relays. This is for the clockwise setting. All the relays associated with the clockwise relay, right? These settings, so these settings are finally we got for relay R1 is 0.0565, for R4 it is 0.0535, for R3 it is 0.0599, then for R2 it is 0.0369. These are the TMS settings for these relays R1, R2, R3, R4, which are considered in anti-clockwise direction, right? Okay. Now we'll consider in clockwise direction. So this is in anti-clockwise direction, right? So this is in anti-clockwise direction. Now again we will consider in clockwise direction and we will find the setting for rest of the relays, that is R5, R6, R7 and R8. So in the by following the similar steps and going through the iterations, when it will converge, we'll find that the final values of R5, R6, R7 and R8. So this is the way of finding the relay settings in a mesh network. It is an iterative process, right? So this is how we found in for fault one for different faults in anti-clockwise and clockwise direction, right? So in anti-clockwise we found the setting for in anti-clockwise we found the setting for R1, R2 and R3 and R4, right? And in clockwise direction we can find the setting for R5, R6, R7 and R8, right? Okay, so this is R8. Okay, so this is how we'll find all the settings of relays. So different sets of relays, that is one set is for anti-clockwise and other set is for clockwise direction, right? So already using this table we can find again for clockwise direction, clockwise relays, the relays associated with the clockwise, the settings of the relays associated with in clockwise direction, right? Okay, so this is all about your directional relay, and in the next class, so this is all about, you can say, your overcurrent protection. Already we talked many classes on overcurrent relay, overcurrent protection, and in the next class onwards we'll talk about uh, the distance relay. What are the drawbacks of the overcurrent relay when it is used in the transmission line, and why it cannot be used in the transmission line? Then we'll see for transmission line what kind of protection scheme we need, and that is in fact we call it distance protection. We'll see in the next class the distance protection. So thank you very much. Thanks a lot for your kind attention.